Good morning everyone. Welcome to Swapna physics classes. Just a minute, I will check my audio and video quality. Yes. Join quickly. Now last class we had gone through the spectral terms, right? Spectral terms. How to find out the spectral terms, right? And I had given you some problems. Did you solve those problems? Somebody asked me to clear this equivalent and non-equivalent electrons. What about the equivalent and non-equivalent electrons? I will explain this again. Don't worry. Let's go with equivalent and non-equivalent electrons. So what is the difference for equivalent and non-equivalent electrons? Okay, let's see. Equivalent electrons and non-equivalent electrons. In equivalent electrons, either N or L values are same. Both the N and L values, are same. Coming to non-equivalent electrons, either N or L values are different. For example, I have SP configuration, PD, DF, and so on configurations. We have different configurations, right, in our electronic configuration, right? SP, PD, DF. For example, I'm taking here both the L values are different. L1 and L2 are different. L1 value is 0 and L2 value is 1. Okay, and in this case L1 value is 1 and L2 value is 2. Here L1 is 2 and L2 value is 3. Okay, and coming to equivalent electrons, for example, I have p square. Nothing but in p orbital we have two electrons. For two electrons we will be having L1 value and L2 value. L1 for one electron and L2 for another electron. Okay, therefore here L1 is 1. Why? Because this electron lives in p orbital and L2 electron also live in p orbital. Therefore L2 value is also 1. So for equivalent case L values are same and non-equivalent case L2 values are different. And how to find out the spectral terms for equivalent and non-equivalent electrons? You have to take all the L values here and all the S values here. Okay, so here in this case what will be the capital L? L is nothing but modulus of L1 plus L2, that is 2, and L1 minus L2, that is 0. Therefore we have 2, 0, 1 here. And here L values are 2 minus 1 is 1 and 2 plus 1 is 3. 3, 2, 1 are the L values. And coming to this, S values are 1 by 2 minus 1 by 2 is 0. 1 by 2 plus 1 by 2 will be 1. And here also S values are 1 and 0. So just to take here, for equivalent case we have L values 2, 1, 0, that is 1, 2, 0, 1, 2, and L values are 0, 1. Okay, and you just now add up. Okay, and the multiplicity for S equals 0 is 1, and for s equal to 1 the multiplicity will be 3. If you substitute 1 in this place and 0 in s place, okay, this will be the multiplicity. Okay, here we have singlet, here we have triplet. For equivalent case, for singlet you have to cancel out all the even terms, and for triplet you have to cancel out all the odd terms. Now find out the j value. 0 plus 0 is 0, 0 plus 2 is 0, and now find the value j value here. 1 plus 1 is 2, 1 minus 1 is 0. Okay, these are the j values. So for singlet case j value is 2, triplet case j value will be 0, 1, 2. This is the shortcut, and write the spectral terms here. For singlet case we have 1, 2 is for here, right, as PD L values. Okay, so 1 for 2, here for 2 we have d orbit and j value is 2, comma, and triplet case we have j, first of all write the L value, that is p, and j is 0, and 3p1, 3p2. These are the spectral terms for p square orbital, right? Here in our p orbital we are having 2 electrons. Okay, and good evening everyone. Thank you for joining my live. Good evening. Okay, so these are the spectral terms we have. And what is the ground state spectral term? First of all, you have to check for the higher multiplicity. Here we have 3 is the higher multiplicity, and then go for L values. So here for 3 multiplicity we are having 3 p values, 3 p orbitals, then go for j. Okay, check for multiplicity initially, check for multiplicity, then check for L values. If L values are same, then go for j values. Okay, go for j values. Go if the orbital is less than half filled, then go for lesser j value. Okay, and or if the orbital is more than half filled electrons, then you just go for higher j value. Here p orbital can be filled with 6 electrons, maximum number of electrons 6, and here you are having 2 electrons, that means it is less than half filled, therefore you have to go for lower j value. Okay, here lower j value is 0, 0, 1, 2. For 0, 1, 2 you are having 0 is the lower j value, therefore the ground state spectral term is 3p0 in this case, ground state spectral term. This is for equivalent case. Coming for non-equivalent case, for example, I having SP configuration, and you just find out L value, S value. Then how to find out this J value? Okay, using the same case. Okay, just find out L value and J value. Here you have to consider all the J values. Okay, for equivalent case you have to consider only odd terms for singlet and even terms for triplet. But coming to non-equivalent case, you have to consider all the terms. Okay, then after you have to check for the higher multiplicity to find out the ground state spectral term, then go for say L, go for L. If L is same, then go for J. If the orbital is less than half filled, then go for lower J value. If the orbital is greater than half filled orbits, if the orbit contains greater than half filled electrons, then go for higher J value. Okay, I hope your doubt is cleared. And coming to our today's class, magnetic dipole moment. Our next topic is magnetic dipole moment. How to find out the magnetic dipole moment? Let's see. Let's find out the magnetic dipole moment. As we know that as we know that an electron revolves around the nucleus in circular orbits with velocity v. Okay, and because of the motion of the electron, we will have the current I in this orbit. And see, if you take the right hand thumb rule, if this is the direction, of the flow of the current, and you just open your thumb, if this is the direction of the current, and this will be the this thumb direction gives the magnetic field direction. Okay, if this is the direction of the current, then this will be the magnetic field direction. Okay, so if this is the direction of the current, you will have the magnetic field in this direction. So from Faraday's laws and Ampere's laws, we know that if there is a current flow, in your coil, then there will be a magnetic field. If there is an electric field, there will be, obviously we have a magnetic field, right? So this will be the direction of the magnetic field. Okay, here we have a charge ZE. In this electric field, in the electric field of the nucleus, an electron is revolving. Okay, and because of the motion of the electron, we will have the flow of the current, and because of this electric field of the electron, we are having the magnetic field. Okay, right. And in the same direction, we will have the orbital angular momentum direction, and in downward direction, that means in opposite direction to this orbital angular momentum, you will have the magnetic orbital angular momentum. To balance the system, we will have the magnetic orbital angular momentum in opposite direction to this L bar. Okay, right. That means that this L bar and L bar are anti-parallel to each other. Now, here we have the magnetic dipole momentum. Here we have ZE and E bar. These charges act as a dipole. These charges act as a dipole. Okay, and coming to the magnetic dipole momentum, L is equal to N into Ia. We will derive this formula in electromagnetic theory. Okay, you just write this formula. We will discuss about this formula in our electromagnetic theory. You just don't worry. This is the orbital magnetic momentum of this electron. As this electron is moving in this orbit, we are having the magnetic field, and the magnetic field of this orbital magnetic momentum is N into Ia, where this N is number of turns. If N is equal to 1, then magnetic dipole momentum will be equal to I into A, where I is the current and A is the area of this orbit. And as we know that the current is equal to charge per time period, is the charge on the electron and it is the time period. And from time period, we know that the time period is equal to 2 pi r by v. Velocity is v, and r is the radius of the orbit. Therefore, if this is equation number 1, this is equation number 2, this is equation number 3. From 2 and 3 equations, the current I is equal to E into V by 2 pi r. Just substitute this third equation in second equation. Okay, and now you just substitute this fourth equation. From 4 and 1 equation, the magnetic dipole momentum UL is equal to I equal to EV by 2 pi r into area of the orbit is pi r square. It is the circular orbit, right? Therefore, this magnetic dipole moment MuL is equal to what is MuL? Here we have you just cancel out this pi r and r. Therefore, EV r by 2. EV r by 2 is a magnetic dipole momentum. Here I am considering the modulus of this magnetic orbital magnetic dipole momentum, and this is equation number 6. We know that. And the orbital angular momentum is equal to mvr. We know this. This is equation number 6. If you divide this equation number 5 with equation number 6, therefore we are having mu L by mod L. Modulus of mu L by modulus of L. We have EVR by 2 times MVR. V cancel, R cancel. It will be equal to E by 2M. And therefore modulus of mu L by mod L bar, mod L or L bar will be equal to E by 2M. And coming to this is a constant value, right? Why? Because mass of the electron is constant and charge of the electron is constant. And this modulus of mu L bar by mod L bar is known as gyromagnetic ratio. Gyromagnetic ratio. Remember this, gyromagnetic ratio. And in vector form, I can write this equation as in vector form. I can write this equation mu L bar equals to E by 2m into L bar. So here I am considering the direction of the L bar and mu L bar. See, if you look at this diagram, this L bar and mu L bar are anti-parallel to each other. That means they are in opposite directions. Therefore, here we will having the minus sign. Here minus sign indicates the direction of mu L bar and L bar. Okay, minus E by 2m times of L bar. And yes, minus E by 2m times of L bar. Here we are having minus sign. And here I am taking GL. GL is a constant which is known as Landé G factor. Landé G factor whose value is equal to 1. It's very important. GL value is equal to 1. Landé G factor. Okay, in the same way, we can also derive the equation for mu S bar and mu J bar. Mu S bar and mu J bar. Mu S bar and mu J bar. Okay, and I just want to derive this mu S bar. Mu S bar is equal to minus GS times E by 2m S bar. Here GS value is equal to 1. Here GS value is equal to 1. Just remember these points. And coming to mu J bar, it will be equal to minus GJ into E by 2m into J bar. And GJ is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2 times of J into J plus 1. 2 times of J into J plus 1. This G, S, G, J, G, L are Landé G factors. Landé G factors. Okay. Remember this. So these points are important for your JL, DL and set examinations. Okay. Remember this. Okay, and going for our next topic. Our next topic is spin orbit interaction. Spin orbit interaction. To find out the hydrogen fine structure, for hydrogen atom fine structure, I am considering the spin orbit interaction. I'm considering the spin orbit interaction just because, as I said just now, electron revolves in the circular orbits. Electron revolves in the circular orbits with velocity v. Okay, and because of the write the points whatever I'm teaching you. All these points are very important. See, because as the electron is moving in the circular orbit, in the electric field of this nucleus, in the electric field of the nucleus, we are having the current I, and as we have the electric field here because of this nucleus, there will be also a magnetic field. As the electron is moving with velocity v, and as we are having the electric field, that means we are also having the magnetic field. If the velocity is equal to 0, then there will be no magnetic field. Do you know this? If the electron remains at rest position, then there will be no magnetic field. There will be only electric field because of this nucleus and this negative charge, that is electron. So as the electron is moving with velocity v, here we are having the electric field because of the nucleus as well as this charge, that is electron. Therefore, we are also having the magnetic field. Okay. If this is the direction of the motion of the electron, this will be the direction of this magnetic field. This magnetic field is internal magnetic field. This magnetic field is a internal magnetic field. Okay, coming to hyperfine structure. Sorry, not hyperfine, sorry, hydrogen atoms fine structure. Coming to the fine structure, fine structure spectroscopy or fine structure spectrum of hydrogen atom. Fine structure spectrum of hydrogen atom. Fine structure spectrum of hydrogen atom. Coming to the fine structure spectrum of hydrogen atom, because of this magnetic field, internal magnetic field, we are having spin orbit interaction, and this spin orbit interaction is a weaker interaction. See, as I said, in LS and JJ coupling, LS coupling for lighter orbits, JJ coupling for heavier orbits, right? Heavier atoms, lighter atoms and heavier atoms. And here I am considering the spin orbit interaction is a weaker interaction. Why? Because here electron having the spin. Okay, therefore because of this spin motion, here we have this spin angular momentum, and as electron is moving the circular orbits, we are having the orbital angular momentum, mu L, mu S. Okay, and because of this magnetic field, what happens? This is a magnetic field. Without magnetic field, the angular momentum, orbital angular momentum orientation will be this one without magnetic field. And because of the internal magnetic field arises due to the motion of the electron, then this will be the orientation of the L bar, orbital angular momentum, and this will be the orientation of the spin angular momentum. Okay, and if you place the atom in, this is due to internal magnetic field, and if you place the atom in the external external magnetic field, if you place the atom in external magnetic field, then this J bar will be oriented in this direction. That means you will be having L bar and S bar in this way, orientation of L bar and S bar, and this will be the J bar. Okay, and here we are going to discuss about the internal magnetic field only. This external magnetic field effect is known as Zeeman effect, right? Zeeman effect and Stark effect will be discussed in our later classes. Okay, and if you have any doubts, please write in the comment section. Good morning, welcome to my class. Yes, And here I consider the weaker interaction. Why? Because here we having only one electron. If you consider n number of electrons, then there will be a strong magnetic field. There will be a strong magnetic field, and you will be having strong spin orbit interaction. Why? Because single electron can generate a weaker magnetic field, but if you have n number of electrons, the motion of those electrons, n number of electrons, will generate a strong magnetic field. Okay, and because of this spin orbit interaction, the spin orbit interaction is responsible for the fine structure spectrum. You just keep it in a bracket. Spin orbit interaction is, write a sentence, spin orbit interaction is responsible for the fine structure spectrum. Because of the spin orbit interaction only, we will be having this magnetic field, internal magnetic field. Okay, so here we will be having the electric field, right? The relation between the electric field and the potential energy is, the electric field is nothing but gradient of the potential energy, and this can be written in terms of d over r by dr r cap in vector form, right? Why v over r? Why I had considered v over r? R theta pi. Here these are the spherical coordinates. Okay, we are not considering this theta and pi. Okay, here the motion of the electron is radial, and this potential energy depends on the radial form of the orbit, right? So here we are only considering v over r, and as we know that this r cap is equal to r bar by r, and this electric field equation will be equal to dv over r by dr into r bar by r. This is a vector form. Okay, this is a vector form, and using this vector form we are going to find out the equation for this electric field. And the relation between magnetic field and electric field from Lorentz transformations. Yes, from Lorentz transformation, this B bar will be equal to 1 by c square times of E bar cross V bar. V is the velocity, is the electric field, B is the magnetic field, and C is the speed of the light, and just multiplying and dividing this equation with M. Okay, and yes, this B bar can be written as 1 by C. Just substitute this electric field in this equation. Okay, then after multiply and divide. Okay, dv over r by dr into r. I'm writing this here, and we left with r bar cross v bar, and now multiply and divide this equation with mass m. Therefore B bar equals to 1 by cr dv by dr into, as we know that linear momentum L bar equals to mvr. Here mv is, here we have mv and r. Okay, r bar cross p bar, magnetic momentum is r bar cross p bar, and p bar is mass into velocity. Okay, I'm just substituting this term, okay, with L bar. Therefore we have here L bar, and we left with mass m. I'm writing here. Okay, keep it in a box. And as we know that the relation between the magnetic field and the energy, change in energy. Let's see. That is delta E. Here there is a change in energy, and therefore I am considering delta E. Why there is a change in energy, I will explain. Okay, minus mu S bar dot B bar. See, all these equations relating to the electric field and the magnetic field and the potential energies are going to be derived in our electromagnetic theory. Okay, don't worry. So there is a change in energy because of the spin orbit interactions. Okay, spin orbit interactions. There is a change in energy, and we will write the change in energy. We will correct the energy equation in our further classes. Don't worry. There is a change in energy just because here we are having the magnetic field, and if this is L bar, this is internal magnetic field, weaker internal magnetic field, L bar orientation, S bar orientation, and this will be the J bar. Okay, this is the J bar orientation about this magnetic field. See, initially without magnetic field, this will be the J bar orientation along the axis, along the Z axis we are having, and these are the orbital and spin angular momentums. Okay, these are the orientation of L bar and S bar. This is the J bar orientation along the Z axis. And if you have the magnetic field B bar along this Z axis, then there will be a deflection in the orientation of J bar. Okay, that means there will be a change in the energy equations because of the spin orbit interaction of this because of the magnetic field, spin orbit interaction because of this magnetic field. Okay, and as we know that mu S value is equal to E by 2m times minus G as E by 2m times of S bar, where this Gs value is 2. Gs value is 2. Therefore, delta E bar is equal to minus 2 to cancel, E by m. We have one more minus sign here. Okay, minus of E by m into S bar into B bar. Now you just substitute B bar. See, I am concerned this is as equation 1. Substitute equation 1 equation in equation 2. Substitute equation 1 in equation 2. Okay, I will take a fresh page. Right. Here, therefore, delta E bar equals to minus into minus plus E by m S bar dot. What is the B value we have? 1 by mc square r into dV over r by dr L bar. Okay, now write E by m square c square. E by, this will be equal to E by m square c square, E by m square c square into 1 by r dV over r by dr S bar dot L bar. S bar dot L bar. Now we have to find out this S bar and L bar. Will you find out this from the total orbital momentum, total orbital angular momentum? We know that this will be the sum of spin orbital angular momentum and orbital angular momentum, right? From here you just multiply you just take the dot products of J with J and S with S and L with L. Okay, L with L. You will be having J square. J dot J will be J square. Why? Because as both these are parallel to each other, cos 0 will be equal to 1, right? As both these are parallel to each other, okay, here J dot J will be J into J cos theta. Therefore theta is equal to 0, sin cos 0 equal to 1. You will have J into J is J square, which will be equal to S square plus L square. Here S dot S will be S into S cos theta. Both these are parallel to each other. Both the spins are parallel to each other, and both the orbital angular moments are parallel to each other. Therefore, we have S square plus L square. S square plus L square. From here, you can write. Yes, so sorry. Just a minute. So J bar dot J bar can be written as L plus S bar dot L bar plus S bar, right? L bar plus S bar. This is the way to write, sorry. So here we are having L bar dot L bar will be L square plus L bar dot S bar plus S bar dot L bar plus S dot S will be S square. Okay, and L bar dot S bar will be equal to S bar dot L bar. Therefore, here you are having L 2 times L dot S plus S square plus L square. This is equal to J square. This is the way we have to write when we discuss about the vector form physical quantities. Vector form of physical quantities. Good evening Mansa, good evening Ramesh. Thank you for joining my live. Thank you so much. Please click on the like buttons. Please click on the like buttons so that I feel that you are encouraging me. Thank you so much for joining my live. Please click on the like buttons. So from here you can find out this S bar dot L bar. Okay. So L bar dot S bar or S bar dot L bar can be written as J bar minus L bar J square minus L square minus S square by L dot S. Take bar over all these physical quantities. Why? Because these are vectors. All these are vectors, and we left with sorry, here we left with 2. L bar dot S bar is equal to 1 by 2. Right now, as we know that modulus of J bar is equal to J H cross into square root of J into J plus 1, and modulus of L bar is equal to H cross into square root of L into L plus 1, and modulus of S bar is equal to H cross into square root of S into S plus 1, and where this H cross value is H by 2 pi. Now substituting all these values in this above equation, that is S bar dot J bar, S bar dot L bar, S bar dot L bar. This will be equal to J square will be, I'm taking H by 2 pi common, that is H square by 4 pi square by, because here we are having square, here we having square. Okay, and this will be equals to and we having divided by 2. I'm taking outside here, so 4 2 ja 8, 4 2 ja 8 into J square will be J into J plus 1 j into j plus 1, j into j plus 1 minus L into L minus 1 minus S into S minus 1, right? Yes. And now you just substitute this equation. You just substitute this equation in equation number. What's this equation number? This is equation number 2. This is equation number 3. This is equation number 3. So you just substitute this value in equation number 3. This is equation number 4. Here we have equation number 4. Substitute equation number 4 in equation number 3. Substitute equation number 4 in equation number 3. So what is equation number 3? We having delta E is equal to E by m square c square, E by m square c square into 1 by R dV or R by dr into S bar dot L bar is, what is the value we have? H square by 8 pi square, right? Into j into j plus 1 minus L into L plus 1 minus S into S plus 1 minus S into S plus 1. And see here, this from this equation, this is varying. 1 by R dou V by dou R is varying, right? Here these are varying, these are not constants. So here I am taking bar over this. I have to consider the average value. Okay, I have to consider the average value. As the electron move to excited state, again it will move to lower states. The R value changes. The potential, here the R value changes, the potential energy changes. Velocity also changes. Therefore, delta E is equal to E H square by 8 pi square m square c square. And not only that, here we are having divided by 2. Just because of Thomson's precision. We will discuss about Thomson precision in our electromagnetic theory. Here energy, coming to energy, here this is divided by 2. Here we having 1 by 2. This is due to Thomson's precision. Thomson's precision of the motion of the electron in the orbit, right? Therefore here we are having divided by 2. Okay, so 8 to just 60. 8 to just 60. Okay, into here into j into j plus 1 minus L into L plus 1 minus S into S plus 1 into 1 by R dV over R by dr. This is, here I am considering the average. So first of all we will find out this dV over R by dr. From electromagnetic theory, we had already discussed about the potential energy. V over R. There I denoted with U in our previous class. You just go through our live class, lecture number 2. Okay, good evening Mansa. V over R is equal to minus 1 by 4 pi epsilon naught Ze by R. Okay, if you take the differentiation with respect to R, here you will be having minus 1 by R is 1 by R square. Therefore, it will be equal to Ze by 4 pi epsilon naught R square. Okay. Now you just substitute this value in this equation. Therefore, this delta E is equal to EH square by 16 pi square m square c square into j plus 1 minus L into L plus 1 minus S into S plus 1 into this 1 by R, I'm taking bar, this means average, into 1 by 4 pi epsilon naught Z E by R square. Okay, as R is varying, I have to take bar over this. These are constants. Okay, I have to write them separately. That is E into E square, Z E square, H square by 16 into 4. 16 into 4 right here separately. I am writing for 16 pi square m square c square into 4 pi epsilon naught into j into j plus 1 minus L into L plus 1 minus S into S plus 1 into 1 by R into R is R cube. Just take the average of this R. Okay, and from generating functions, from quantum mechanics, you will derive this. From generating functions, this 1 by R cube, average of this 1 by R cube is equal to Z cube by A naught cube into N cube into L plus 1 by 2 into L plus 1, where L is greater than 0, always greater than 0, where A naught is a smallest orbit. Okay, radius of the smallest Bohr's orbit. Yes, and its value is A naught value is A naught. Bohr's smallest orbit value is equal to 4 pi epsilon naught h square by 4 pi square m e square. Okay, if you substitute these values, that is the average of 1 by R cube and A naught values in this above equation, the energy equation will be equal to, see, you just solve for this energy equation will be equal to R infinity, that is Rydberg constant. What is the Rydberg constant? M e power 4 by 8 epsilon square s square c, right? You just to take the common values here from here and write the Rydberg constant. Okay, R infinity alpha square is a spectrum constant, hydrogen spectrum constant value. Okay, 1 by 137 is the alpha value. Okay, alpha square z power 4 hc by 2 n cube L into L plus 1 by 2 into L plus 1. Okay, this will be j into j plus 1 minus L into L plus 1 minus S into S plus 1. You just substitute 1 by R cube and A naught values in the energy equation and solve for this equation. Okay, and this alpha value can be will be 1 by 137 when you substitute these constants by 2 epsilon naught hc. Okay, this is fine structure constant. Fine structure constant whose value is 1 by 137. Okay, so this will be the energy equation, that is change in energy equation due to spin orbit interaction. And the term value, coming to the term value, if you divide delta E with the hc, this will be known as the term value. Okay, this will be equal to, see, if you just divide this equation with hc, therefore HC cancelled. Now you just write the remaining terms, that is minus R infinity alpha square z power 4 by 2n cube L into L plus 1 by 2 into L plus 1. See, these equations are very important equations. We are going to solve problems using these equations only in our next class. So don't skip the solution. Don't skip this derivation. All these equations are very, very important equations. Using these equations we are going to solve problems. Okay. And we know that for single electron, for one electron, S value is 1 by 2. S value will be 1 by 2, and if we don't know where this electron is situated, therefore I am taking L as L, and J values can be from modulus of L plus S to modulus of L minus S. That means J value is L plus or minus 1 by 2. L plus or minus 1 by 2. And here what you have to do is, see here we have only one electron, and therefore I am considering only one value, that is J values is from L plus or minus 1 by 2. Sorry, here we have only one electron. Okay, yes, this is modulus, and you just take this value, that is J into J plus 1 minus J into J plus 1 minus L into L plus 1 minus S into S plus 1, and substitute the J values. J equals to L plus or minus 1 by 2. Okay, you just substitute this equation in this equation. Okay, for L plus 1 by 2 and for L minus 1 by 2. Okay, in place of J, you just take L plus 1 by 2 for ones and L minus 1 by 2 for ones. Therefore, here this above equation will be equal to L and minus of L plus 1. You just solve this. As time is running out, I am not solving this. You just substitute these values. First of all, you just substitute L plus 1 by 2 in this above equation. Therefore, if you substitute L plus 1 by 2, then you will be having L. If you solve this equation by substituting L plus 1 by 2, you will be having L. And another time, you just substitute this L minus 1 by 2, and therefore you will be having minus of L plus 1. Okay, that means L is divided into two terms. Okay, this is the responsibility, that means L as orbital interaction is responsible for fine structure splitting. That means one orbit is split into two orbits. So if you substitute these values, that is, this is J, if you substitute L and minus L plus 1 in place of this equation, in place of this value in the equation, okay, in place of this, if you substitute L for ones and minus of L plus 1 for ones, therefore this term value delta T will be equal to minus R infinity alpha square z power 4 by 2n cube L times L plus 1 by 2 times L plus 1 into L, and one more value is, here it is, I'm taking prime, double prime here. Okay, minus R infinity minus plus 1 alpha square z power 4 2n cube L into L plus 1 by 2 into L plus 1 into L plus 1. these are two term values we are having. That means one orbital, that means one orbital is split into two orbits. Okay, that means here if this is initial j value, therefore after splitting you will be having j1 and j2. Okay, if the transition takes place from some p orbit to d orbit, okay, d orbit will also split into two orbits. Therefore, if the electron lies in this orbit, okay, that means we don't know where the electron is actually in these both of these j1 and j2 orbitals. We don't know where is the electron. That means here the transitions, number of transitions from one orbit to the other orbit increases, from p to d increases. Okay, so initially we are having if this is p and d, initially we are having only one transition, but because of these spin orbit interactions we are having four lines here, four transitions. That means in spectrum, instead of one single line, we are having four lines. This is nothing but fine structure splitting of the spectral lines. Fine structure splitting of this spectral lines. So I will discuss about this fine structure splitting. Fine structure splitting of the spectral lines. Okay, of spectral lines in our next class. This is a very important class. Why? Because there will be one question for your CSIR NET, UGC NET, and GATE exam, SET exam, JL and DL. There will be a definite question from our next class. From our next class, we are going to have a definite question for this examination. And whoever didn't subscribe to my channel, please subscribe to my channel and share with maximum number of people. Okay, bye.